Back to the Bessel functions. In this short video, I like to collect a few properties of the Bessel functions. Here you see them again. On the left, you have the first kind. On the right, you have the second kind. And you know the first kind are regular. They look more like sine or cosine. On the right, the second kind functions have a singularity at 0. Let's look at the asymptotics. So the asymptotics, I mean the limits. For example, here I look at the limit as x goes to 0. So what happens near the origin? The 0 Bessel function is 1. The lambda Bessel functions, they have a certain profile following x to the lambda. They look like a polynomial close to 0. For example, if lambda would be 2, then this would be some coefficient times x squared, x to the 2. So here's a good time to explain the gamma function. There this gamma of 1 plus lambda appears, and the gamma function is a very particular function, which I show right here. All right, here is the gamma function. So it's defined as the integral from 0 to infinity, t to the x minus 1 e to the minus t dt. It is a common function. You should maybe see it like the Gaussian. The Gaussian is a well-known formula, or the error function is a formula which we might use later. So here this is called the gamma function. Back to the asymptotic formulas, you see that y0 goes to minus infinity, and here you can see it goes like the logarithm. The logarithm goes to minus infinity as well. And the j lambdas, they go like 1 over x to the lambda, so they diverge also like a rational function. For large values of x, as x goes to infinity, and this is really cool, they behave like cosine and sine, and this is what I wanted, right? So that the j lambdas behave like cosine of a strange argument, x minus pi quarters minus lambda pi half. But anyways, in the sense, if you look for very large x, it's a cosine, and the y's for very large x will be the sine. For sine and cosine, we know that if we differentiate cosine, we get minus sine. If we differentiate sine, we get cosine. And similar here, if we differentiate the Bessel function jn multiplied by x to the n, we get the Bessel function jn minus 1 multiplied by xn. And similar for a negative exponent. So there's also relations between the derivatives of these Bessel functions, a little bit similar to sine and cosine. How about integration? Integration also gives us a nice formula. Here, jn can be written as an integral. It can be written as the integral 1 over pi, integral from 0 to pi, cosine of n theta minus x sine theta d theta. Another fun thing we can do is corollary 6.3, where we can actually write the sine and the cosine as Bessel series. These are called Bessel series because it's a series of Bessel functions. And it turns out the sine can be written as a series of the odd Bessel functions, whereas the cosine is a series of the even Bessel functions. Beautiful formulas. Now let's look at the zeros of the Bessel functions. Remember, they were highly oscillatory, so they have a number of zeros. And the zeros now I call Zmn. So I take the Bessel function with the index m, and this Bessel function Jm has the zeros Zm1, Zm2, Zm3, and so on. So that Jm at Zmn is 0, and n is the counter for the number of the 0 along the line. And if we take these zeros, we can get an orthogonality relationship. If we take a fixed integer m, so we take a fixed Bessel function Jm here and here, and then we have these different zeros, right? Zm1, Zm2, and so on. So we take one of the zeros as argument Zmnx here, and another one with a k, Zmk times x there. Then these are orthogonal, means the integral is 0, with the weight function x. We have learned earlier that for orthogonality we can allow weight functions. Also Sturm-Liouville problems use weight functions. And so if you take a Bessel function and take two different zeros, Zmn, Zmk, then these functions are orthogonal. Again, let me just relate this to the sine, right? If we had sine n pi x divided by L, and we had sine of k pi x divided by L. If n and k are different, then these functions are orthogonal.